SwayamPrabha. Digital India. Educated India.
Hello and welcome to this lecture of elements of mechanical vibration. The previous lecture we got introduced to the basic philosophy. Today's lecture is going to be devoted to finding the response to a transient excitation or an arbitrary excitation. So, what we should now try and understand is that even if we get an expression for such a unit impulse excitation to a simplified vibratory model, whose response we already obtained as given by this expression. This is with the assumption obviously is that the impulse acts at time t is equal to 0 for a short duration dt, and we assume that the response begins immediately after the completion, and so this dt being too small, it does not really matter whether it starts from dt or from t is equal to 0, but the response obviously is a harmonic sinusoidal waveform starting after the application of the impulse. But we already knew that our excitation function actually is an arbitrary excitation as seen here, and we only found out how the response would look like for the first impulse, which could be given by this. What about the impulse that acts at a later time? For example, after some initial impulses, if we are focusing on this particular impulse which is happening after tau period of time. So, the impulse here has a force value of f at tau, and if this impulse is to be considered for its for the response of the system, then this equation as it is cannot be valid. Why is that not valid? Because it tells us that the response is at time t, which is recorded from this initial t is equal to 0, and therefore, if the response is found using this expression for an impulse which is not starting at t is equal to 0, we may end up predicting that the response is given by this value. However, if this impulse happens after a tau period of time, then we notice here that instead of the response being this value which we saw earlier, the response at time t is actually this value. Okay. So, a completely different value of the response or the instantaneous response value is obtained if the time parameter is not properly scaled to map the value of the impulse acting at the position tau. Okay. So, therefore, what we would like to now do is to account for the position of the impulse at a later time tau by shifting the time scale, and that basically means that instead of finding out the response at t by using in this function the value of time as t, the response obviously has to be at this point, but then to evaluate that sinusoidal function here at this point, we will have to shift the times axis, and the time value should be t minus tau. Okay. So, then only you will be able to use this expression to get this particular response. Okay. And that is how we do it. We modify this equation by shifting the time to t minus tau. Okay. And obviously, f cap dt is now going to be not a constant value, it has to reflect the value of the force at the period at the time tau. So, this tau is going to be a variable that will define which particular impulse are we talking about. So, F cap tau is actually the force or the force value of the impulse happening at the time tau, and because this is going to be our integration variable or the variable in question, and instead of dt we are going to use d tau. Okay. So, this width is going to be in time is going to be d tau. Okay. So, rest of the expression remains the same, and of course, as we discussed, instead of time t it is going to be t minus tau. Okay. So, the response is if we use this global time, that is starting from t is equal to 0, we will end up erroneous getting erroneous value for all the impulses that are happening after t is equal to 0. So, so we shift the time axis as we saw here, and of course, accordingly our impulse response function is going to change. The unit impulse response function with a time shifted function is going to be sin omega and t minus tau here, and this basically is then the modified expression for the unit impulse response function. With this, we can now explore as to how do we take the response of the system for all such impulses which are going to come one after the other. But before we do that, let us look at how the unit impulse response function for a damped vibration case or a system having damping has to be modified. Of course, the modification is going to be quite simple. This is the expression we already have for an undamped case, but for a damped case we already know that the exponentially decaying quantity has to appear, and that really has to be the part of the solution process. The instead of omega n we will have the damped natural frequency appearing in the expression, and therefore, the response to unit impulse for any arbitrary impulse appearing after tau period of time will be given by this expression. So, the impulse response function will appear like this. So, you multiply this with the actual impulse value, that will give you the total response that we have already seen. Okay. So, we have seen an excitation which is a transient excitation, and how the total transient excitation function can be made up of multiple impulses acting one after the other. Now, let us take an actual example of how the response is obtained with this background, and what we are going to consider here is the case of an overhead tank which is modeled like a spring mass system. We keep the damping out for the current discussion just to simplify the process of evaluation, but you can as well include the damping term and modify your unit impulse response function accordingly. But discussion of the undamped case will help you figure out what is the actual process involved, and then with small modification you can apply it for a damped vibration case. Okay. So, the function that we are trying to evaluate here as a forcing function is a triangular wave here. It is presumed that there is some kind of either you can treat this to be a blast excitation or a foreign object impacting on the tank laterally. Okay. So, that generates the transient excitation as given here for a short duration t1, and so the force suddenly rises to a value of A and then suddenly will drop to 0 value shortly. So, with this simplified excitation function, let us look at how we find the response of the tank to such kind of a transient excitation. We may discuss as to what is the response at any arbitrary time, maybe this even before the completion of this excitation, or we may find out the response at time t, which is somewhere here past this particular point. And for a general case, I would of course be also interested that after the excitation is over at certain distant time, how is the vibration happening. Obviously, the amplitude which is here will continue to be the same here, but that is what we want to know as to how the amplitude is going to be after certain period of time t at different locations. So, we may be finding it out before appearance of this largest value of the amplitude, or little later as well. Okay. So, with this example in mind, let us look at how the response estimation goes. Okay. So, let us look at any arbitrary excitation shown here as a triangular excitation function, which as we discussed can be approximated by a set of or a series of impulses of the strengths which are going to change over a period of time. Now, just for the sake of simplicity, it is shown triangular, but I can as well take into account any arbitrary excitation, and for this also arbitrary excitation I can discretize and use it as a piecewise linear. In this piece, this has a constant amplitude. Okay. So, we have discussed how the response to a solitary impulse taking place at tau instant of time can be obtained. So, the response to that, how it is to be obtained, that we have discussed. Now, the job here is to figure out how do I add up the responses of each of these impulses happening one after the other over a period of time. Okay, that is the whole job here. So, for doing that, what we say is that if I suppose want to find the response of the system at time t, which is before this value. So, before this, if I want to find out the response at this because of the excitation which is going to be like this, okay, linearly changing. So, the idea is I will discretize this into multiple such parts. So, one of these parts may be like this. So, one impulse is located at a time tau with the step time d tau. It will generate its own response, right. So, we have discussed the sinusoidal function x of t which is equal to f cap d tau over m omega n sin omega n t minus tau. That is the response expression that we have already derived for a solitary impulse having a value of f cap d tau. So, if I know how much is the strength of this impulse, I know how much is the response due to that impulse, and that response will start from this point onwards. Obviously, the response of the system will start from where the impulse is applied in time. Okay. This t is still a global t, that means I am still talking about this time. This tau is the position of this impulse where it is located. Okay. Now, that is how the response will look like if I consider this yellow colored part of the total excitation function. Now, if I take so this is now if I take the next subsequent impulse, that means piecewise linear, meaning that even if there are small changes here, I assume it to be constant of certain amplitude, and now after this impulse accounted for, now I will check the response due to this impulse, which is following the impulse shown in yellow. Obviously, what will happen? The strength of the impulse will slightly change, it is increasing. So, the amplitude will change, but unit impulse response function will be same except its time shifted location. So, the response due to the new impulse having a higher value will generate a slightly higher response starting from the end of this impulse. That is what we have done. The initial condition of velocity following this particular impulse was used to derive the general response of the system subjected to initial conditions which was obtained based on the strength of this impulse. Then what? Maybe another impulse, it will generate its own response, but that response will obviously start from here, is not it, and it will have its own amplitude which will be governed by the strength of this impulse, which is going to be governed by the way this function is changing. And now what we do is, we assume that you would have accounted for similar such impulse functions before this and after this up to this point, right. Now we invoke one of the most important assumption here is that we assume that the system is linear, okay, and if the system is linear we can safely add the response due to individual impulses. Okay. Principle of superposition is valid here. With that assumption of a linear system, the total response at this time t will be summation of this response plus this response plus this response. At this time I can keep on adding the responses due to all the impulses that happened before this. Okay. What in the figure I have not shown the responses because of the impulses in this period, just for the sake of clarity or explanation purpose. But just like x1, x2, x3 are added up at a particular time, you can add the impulses which happened just before them. So, the idea here is keep adding these individual impulse responses and then find the total response. Now, here it should be clear in your mind that either you find the response at the end of this impulse, okay, and take that as an initial condition for finding out the response at the end of this impulse, okay, one by one, or assume that they are all independent impulses with 0 initial conditions and simply add all of them up. So, when you use the initial condition of the previous impulses for finding out the response due to this next impulse, you need not add x1 and x2 for finding out x3. But what we have done is we have got expressions of these x1, x2, x3 with the assumption that nothing happened before them, the system was stationary. Therefore, the response due to each impulses can be simply added up together to find the total response, right. So, there are two approaches. One is keep on feeding the response prior to that impulse as an initial conditions to find the response due to that impulse, or you assume that nothing was there before, individual impulse response you find out and simply add them up. That is one and the same thing as long as the system is linear. That is why you do not need to consider what happened before a particular impulse, right. So, this is how we find the total response of the system by adding up responses due to individual impulses, and in general it is the summation of all the impulse response functions scaled or multiplied with their individual impulse strengths like f cap dt, f cap tau dt or d tau, and this is how the summation would look like. So, each of the impulse multiplied with the impulse response function h t minus tau has to be used to ensure that in the global time t, the position of that impulse is appropriately located. And yeah, so this is how it should look like. Okay. Now, as this d tau approaches 0, we know that this summation will change to an integral, is not it. So, as we can discretize these individual impulses and then add each of these responses as a summation series, but if d tau approaches 0, we can as well write this summation to an integral, and then this becomes f cap tau h t minus tau d tau, and that is basically the integral that we have. Summation has to happen from 0 to t, because if you are interested in finding out the response at this time, the contribution to this response would only occur from all the impulses prior to that. Anything that happens beyond this has no role to play, and therefore, the summation of all the impulses before t would contribute, and therefore, it has to go from 0 to t, and that is how this convolution integral is helpful for us to get the response to any arbitrary excitation. Here, just for the sake of illustration, I have shown a triangle, but you can imagine that it can change to any arbitrary excitation. Now, we know that from our discussion that if I want to find out the response at any time t, it will be contributed by individual impulses happening one after the other, and the response due to each of these impulses are simply getting added, assuming linearity or the system being linear. Please do not mind this gap, that is superficial in the sense that they will all come one after the other, and then they will all contribute to the total response at time t. Now, you would all agree that what happens after this has absolutely no relevance to the response happening at time t, because this has yet not been applied. So, all the impulses that occur before this are only going to get to be added up, or they will all contribute to the response. So, this integration limit which actually was initially a summation sign, but we said that if dt or d tau is approaching 0, then that summation converts to an integral, and that is how this integral, which is commonly called as the convolution integral or Duhamel's integral, actually gets used in this particular case. Okay, the blast loading which we mentioned in our introductory part is having an amplitude equal to a, which happens after reaching a time t 1 by 2 from the start. So, our time starts at this point because there is no loading before that. So, the whole tank is stationary as such. The blast happens for a total time of t 1, and it reaches its peak value in t 1 by 2 and then subsides in the rest t 1 by 2. So, if that is the case, how do I evaluate this? Now, for that the impulse response, unit impulse response function has a very standard expression, and again we are assuming that there is no damping. Okay? The concrete columns that are there supporting the mass are assumed to have no damping. So, h t minus tau is 1 over m omega n sin omega n t minus tau, that is our standard expression for this unit impulse response function. Okay. Now, all of these parameters will be known, because if you know your system, concrete tank has its own mass, the columns can be you can use basic solid mechanics to find out what is the lateral stiffness of these columns. So, the value of k, m and obviously then omega n all will be known. You know at what time you want to find the response. So, this is presumably known, and tau is a variable that is going to keep changing. Now, what is f cap tau? Now, this f cap tau is the force at a particular instant of time tau. So, tau is being measured from this 0 time, and this is your integration variable, or the variable at which the excitation force is going to change. Now, for this particular triangular excitation wave form, we can mathematically define f cap tau. Okay. Ultimately, if you want to find out x of t, you will have to do integration on this expression, which means that this is mathematically well defined and known, whereas f cap tau has to be written in a mathematical form, so that you will be able to integrate the expression and get a final expression x of t, because then only you will be able to find the response at any instant of time t. So, to do that, this is how we formulate mathematically this triangular waveform, that before t is equal to 0, obviously there is no excitation, and at this instant I mean in this period starting from 0 up to this particular point of t1 by 2, the force changes linearly. So, therefore, you can say that if this is the amplitude reached, that is equal to a multiplied by t over t1 by 2, because this time is t1 by 2. That is how the force F cap is going to continuously change. Okay. Now, this t actually should change to tau. Okay. So, in this expression it is all written as t, but this has to change to tau. Okay. So, it is going to be a tau over t1 by 2, and that is how it will get defined, that the amplitude at any instant tau from t is equal to 0 will have an amplitude equal to 2a tau over t1. And in this particular region where the amplitude keeps dropping to 0 from t equal to t1 by 2 to t is equal to t1, the expression changes to this. So, in this time period the expression is slightly different, and obviously beyond time t greater t equal to t1, there is no force that acts. Now, with this definition of f cap tau in mathematical terms, we can solve this for two or three different cases, in the sense that suppose if I am interested in finding out that the response at this time t, which happens to be lower than this value, then how do I assess or how do I find this expression for this response? Now, obviously f cap tau equal to 2a tau over t1 should apply, and therefore, if I substitute for f cap tau in this expression, this is how f cap tau gets replaced, and the unit impulse response function as we have been using will take the place of h t minus tau. And now, what you can notice that the integration variable tau is appearing in two different terms. So, you will have to solve this by integration by parts. Okay. So, that exercise is pretty straightforward, you can do that. So, when you solve this, what are the constants here? The constants are 2a. Is t1 a constant? Yes, t1 is a constant value, it is a part of the total time of the excitation, which is for fixed value. So, t1 is constant, m is constant, omega n is constant. So, then what you have is 0 to t tau sine of this has to be omega n t minus tau. Okay. So, and d tau is going to be the total expression. You can solve this by integrating by parts, and once you do that, you get an expression which is going to look like this. Okay. All right. So, this is valid for the response obtained at any time before T1 by 2. Why? Because the expression for f cap tau is obtained based on this linear variation in the force. Okay? The mathematical expression that you use for f cap tau is this, and therefore, that is valid for t any t that is less than T1 by 2, that is this particular half time. Okay. So, this expression is valid for any time t which is greater than 0, but less than equal to T1 by 2. Okay. Now, let us look at how the response can be obtained for a location in time which is beyond this half time, but less than this particular time. Sometimes you may need to find this out, and apart from that, what we are essentially discussing through this is a clear idea about how to use appropriate terms, how to take integration limits. Those are very important things in this particular case. So, even if most of the times we are interested in finding out the response at any time t beyond the application of the excitation, this process will help clarify certain issues or doubts as to what integration limit one should take. Now, as you see here, if I am interested in finding out the response at this instant of time, I will have to take into account all the impulses that happen before reaching to this particular instant of time. Why? Because this impulse will contribute, this impulse will contribute, this impulse will also contribute, and this impulse will also contribute to the total response. Now, we cannot take one single expression to define the total variation of the force right up to this point. So, obviously, in this particular case, when t is lying in this range, then we will have to use two integrals, separate ones. One to take into account the contribution of all these impulses, which is defined through a different mathematical expression, and followed by the contribution from all impulses, which is defined by some other mathematical expression. So, therefore, what we do is we split the total integral or split the total contribution into two different integrals, as we see here and in here. So, this part will be given by this, but if you have noticed, make a note of the limits of integration here. It is not 0 to t as it was done in the earlier case. Why? Because when the time was required to be considered to be this point, then the integration has to go from 0 to t, because all these impulses are to be accounted for in finding the response. But when now the time is up to this point, we are essentially splitting the total integration time for the era which is this and the era which is this, and for this particular integral the limits should go from 0 to this t by 2, sorry T1 by 2. So, therefore, the integration limit is from 0 to T1 by 2, and therefore, the first integral will have a different integration time limits. So, 0 to T1 by 2, and then you can notice that this is f cap tau and the unit impulse response function, and then added to that the contribution coming from this part of the total excitation. Okay. Now, for this f cap tau has a slightly different mathematical form, as you can see here, and so that is getting replaced, followed by the same in unit impulse response function. Now, look at what is the integration limit here. Now, integration limit will start from this to this, because if you are trying to find out or assess the response at this instant of time, all the impulses before this will get added up, and therefore, partly up to T1 by 2 they are added here, and beyond T1 by 2. So, the limit will start from T1 by 2 to T. So, that is your T value. So, this is your T. So, it has to go from T1 by 2 to T, and then this f cap tau is which is applicable for this particular slope of the forcing variation will take its place. So, I hope now this is clear as to what integration limits one should take. Do not also confuse between time t and tau. Tau is the integration limit, integration variable. So, tau is changing as these individual impulses are accounted for, whereas time small t is a fixed time at which you are interested in finding out the response, okay, and the integration limit is d tau. So, this has to be very clear, otherwise there is a common mistake and major confusion most of the time in students mind as to what variable they should be using and what integration limit they should be making use of. So, as long as this figure is clear and you know what you are doing in terms of where the impulses are located, within which time limits, the expression is straightforward to get. So, if as long as you have clarity on what this convolution integral mean, getting this expression is not a big deal. And once you get this expression, solution, further simplification of this by solution of integral is again mainly a mathematical process, no as such conceptual understanding of vibration theory in any case involved here. So, if you solve these equations, these two different integrals, final expression you can always get. So, final expression would be in terms of the mass, the natural frequency, the amplitude A, and of course, the time for which this excitation acts, that is T1, because tau will get replaced by T and T1. Okay. So, this is how the excitation response to transient excitation or an arbitrary excitation is to be observed. If as a last part, if practically more relevant here, that if I want to know what is the response at this time rather than finding out within this excitation period, that is T1, how do I get it? Now, that again follows straightforward from the earlier discussion. For time t which is greater than this T1, again the integration will be similar to the earlier case. So, we will again split it into three parts. Now, one is up to this point, which is T1 by 2, then up to time T1, and then followed by the remaining time here. So, what we see here, from 0 to T1 by 2, this expression is valid. From T1 by 2 to now T1, not T, but T1, because all these impulses will completely contribute, and so therefore, this integration has to go from T1 by 2 to T1, and for which f cap tau is different, and this is same thing which we discussed last time. So, instead of this integration limit going from T1 by 2 to T1, which was the case up to this point, it will go right up to T1, because for a time considered at this position, all the impulses up to T1 will apply. And then for the remaining part, because you need to find out response at this point, all the impulses before this will get added up, but the point is the force does not exist beyond T1. So, even if the integration has to go from T1 to T, the force itself or the impulse itself does not exist. So, it is 0. So, this expression, the third quantity, is actually not there at all, right. So, if you want to know the response at any instant of time t, all the excitation before t will get its contribution to the total response. So, solution of this is again by solving these integrals, and expressions are quite easy to get, particularly if the mathematical function that defines this force variation is simple. Okay. If this instead of a triangular waveform, if you have a sinusoidal or a half sine, which is typically used for representing let us say an impacting force, a half sine wave, then your f cap tau will take the form, if suppose this is again capital A, then it is going to be A sin omega, omega t. Okay. Now, of course, t you will have to see what variable you want to use it, but what will be omega in this case? Omega is not omega n, this is not related to your vibratory system, it is an external excitation. So, omega would obviously be what? 2 pi over total time. Now, total time is going to be 2t if t is the half time, okay, of the sine wave. So, pi over capital T will become your omega. Okay. So, if instead of a triangular waveform, if you have a half sine pulse, then f cap tau will have to be accordingly taken. So, instead of this linear function, you will have a harmonic function and there will be product of two sinusoidal sine functions, and then accordingly the integration will have to be carried out. But I think what is important and to be kept in mind is appropriately capturing this mathematical expression of the force variation and taking appropriate integration limit, because this is the most important part. If you make a mistake here, then the resulting expression will be erroneous. Now, having discussed the response of a simple vibratory model to an arbitrary excitation, the excitation maybe, for example, this is a blast excitation case which can be modeled simplistically by an expression given there, or it can be a simple triangular waveform for a very short duration. It is again an approximation of the actual excitation, but what we are saying here is that even if there is a slight deviation from this kind of an exponential curve, we may be able to approximate the response by capturing the variation of the force in terms of some mathematical function as we see here. Whenever and we have seen in the example as to how this part can be captured mathematically, this part can be captured in the form of a simple mathematical expression. So, even if the response may go up like that, we may be able to get the response with a reasonable accuracy. But sometimes the excitation function could be quite an arbitrary one. Now, in this case also maybe we can treat this to be a set of such rectangles happening for this duration, and then this can be treated as a rectangle, this can be treated as a triangle, and we can make up this arbitrary excitation in terms of these these rectangles or discretizations. But you can get an accurate estimate of this response for an arbitrary excitation by numerically evaluating this. So, instead of some mathematical expression that we have seen how we use it for this kind of a triangular waveform, we may discretize this into such a very fine time intervals and then simply sum up the total response doing it numerically. So, using the numerical addition of individual response expressions, we can find out the response to a truly arbitrary excitation. That is the advantage of this particular method, that it can take up any kind of excitation which may or may not be represented mathematically. Okay. So, that is what is an important aspect here to note. Okay. So, for a vibratory system, the excitation that we discussed till date is in the form of initial perturbation or initial excitation at t is equal to 0. That is what by using initial displacement and initial velocity, these two conditions we considered this. So, an example of that was, like a step dip to any vibratory system, which either generates an instantaneous initial displacement or initial velocity, depending upon the example or the case in question. So, for example, if this is modeled like a spring mass system, exactly at this particular instant of time, there is an initial displacement condition that we typically introduce, and then because of these initial condition, what is the response of the vibratory system, that is what we considered. So, this is like initial excitation at t is equal to 0, and that generates the response. The other type of excitation that we discussed a few lectures back was arbitrary excitation. Now, that arbitrary excitation is not really a sort of an initial condition at t is equal to 0, but it persists for certain duration of time. So, this time is not infinitesimally small. It persists for a reasonable period of time, and it may or may not be captured using some mathematical form, and we discussed how numerical approach can help us evaluate the response to such an arbitrary excitation. Essentially, this arbitrary excitation case was actually stripped into the case of initial perturbation by considering series of such initial excitations through the impulses. Okay. So, this was the second type of excitation that we discussed for a vibratory system, wherein short duration transient excitation like a blast load on the concrete tank or any other mechanical system like a hammer, impact hammer, which is a vibratory system, the excitation could be of transient or arbitrary type. The most important part is that this time is finite and the excitation does not really repeat. So, it is different from the initial excitation case, but it is definitely different than the other common types of excitation, mainly the excitation that is sustained. For example, some of the examples that we considered were that of a tappet valve mechanism in an IC engine, wherein this as a vibratory system was excited through the cam, and as the cam rotates, the tappet valve will be pushed up and down in a fashion which cannot be defined through this kind of a arbitrary transient excitation. Similarly, we considered the case of a wind turbine nacelle rotor, wherein the rotation of these blades generate again excitation which is sustained, and in this particular case will be in the form of a harmonic excitation because of the residual unbalance in the blade system. So, such a vibratory system, when it is subjected to excitation force or excitation displacement, which is time varying and sustained, we need to now look at how the response to such excitation of a simple vibratory system can be estimated or found. Okay. So, I hope it is clear now, the initial excitation case, the arbitrary or transient excitation case, and now finally, we are migrating to a more realistic and more commonly observed excitation source, which is a time dependent sustained excitation function. Now, out of those sustained excitation function, the most common one and the most easier to address is the harmonic one. Okay. So, something which is given by f sin omega t or f cos omega t. So, this is so if this bladed rotor spins at a speed of let us say omega radians per second, because we know that the unbalance rotates with the same frequency as the rotation frequency, and therefore, it varies harmonically with the same frequency omega as the rotational frequency. And here F is you all know that is given by me omega square, the unbalanced force. So, the excitation force F, whose magnitude is this, and it fluctuates with the frequency of omega, which is the rotational frequency in this particular case. The excitation function f of t, the time dependent forcing function, is given by f sin omega t, and it is typically called as an external excitation because neither the amplitude of force nor its frequency has anything to do with the system in question. So, system parameters like k, m, they are independent of or the excitation function is independent of those parameters and is truly an external excitation. And so, the job now is to figure out the way we found expressions for finding out x of t for as a vibratory response of such kind of a vibratory system. Here also we are interested in finding out what is the response x of t of this vibratory system when it is subjected to external forcing function given by something like this, a harmonic excitation function. Typically you might as well find excitation function which may not be exactly harmonic, right. So, for example, in an IC engine the excitation torque to the crankshaft could be like this, although it will repeat perfectly after a certain period of time depending upon whether the engine is 2 stroke or 4 stroke. This excitation torque will repeat itself, and then the excitation is still a sustained excitation, but we cannot or may not be able to use this expression to represent the external force or torque on the system. So, then we resort to something else, and that also is a part of discussion in this response to external sustained forcing function. But we shall take that up after we have extensively explored the response to harmonic excitation. So, this type of excitation because it repeats a certain period of time is periodic excitation, which is going to be discussed and dealt with once we are done with the excitation which is harmonic in nature, because of the fact that getting expressions, getting the response to harmonic excitation case is mathematically straightforward and more simpler, and the response to periodic excitation is a natural extension, and we shall see how we can use all what we learn through this response to harmonic excitation to get the response to periodic excitation. So, that is the topic of discussion in next few lectures. Okay, so, when we say response to harmonic excitation, the right hand side which used to be set to 0 in our earlier discussion of the governing equation of motion for a single degree of freedom system, we usually keep the right hand side term equal to 0, and then started with response to initial condition. We extended that to arbitrary excitation, keeping right hand side equal to 0, essentially 0 in the solution process. In this case the right hand side is non-zero, and that can take the form in different ways, but one of the common form as we discussed can be f cos or f sin omega t. Okay. Now, the examples are like an electric motor which is spinning at certain speed supported on these bearings, and we discussed this example which can be modeled in a simple fashion like a simple shaft, a flexible shaft and a rigid rotor at the a disc at the center of the span, and the bearings offering a simple support, which itself can be modeled like a spring mass system. And then if that is modeled like a spring mass system, if we consider the vibration in the horizontal plane, then because of the stiffness of the shaft, the rotor can be assumed, or a disc can be assumed to be a lumped mass here. This is representing the shaft stiffness, okay, and maybe some damping can be assumed in the shaft material. And then this becomes again a single degree of freedom system, which will be subjected to a forcing function because of the unbalance created by this residual unbalanced mass. Okay. So, all practical rotors cannot be balanced to 0, it will always have some residual unbalance, and that unbalance will create excitation to the shaft rotor system, or a rotor bearing system, so to say, and that f of t can be modeled like a harmonic forcing function f cos omega t. Now, there are ways in which this forcing function is represented. It is, as I said, can be represented as f cos or f naught cos omega t. F naught is the amplitude of the force. Now, that f naught can be any value. In a rotating unbalanced case, it can have a numeric value or an amplitude equal to m e omega square. E is the eccentricity of the unbalanced mass, this is an unbalanced mass, and that amplitude can be given or obtained numerically using these terms. So, it will be fixed for a given operating speed. The other alternate way is to represent f cos or f naught cos omega t as a real part of a complex forcing function, which is given by f naught e to the power j omega t, because we know that this part can be written as f naught cos omega t plus j sin omega t. And if I take the real part of this forcing function, I get back this particular expression. Now, either ways you can solve the equation either from the first or from the second equivalent expression, but for the sake of mathematical simplicity, we will use the second of the two equations. Okay. All right. Before we do that, a small assumption involved here, as we already have discussed, that most of our vibratory systems vibrate with small amplitude of vibration. So, we assume small amplitudes of vibration, and it also has implication in another assumption that the system is linear. Okay. So, systems are typically considered linear when the amplitudes are small enough, so that your force restoring force to displacement or vibratory displacement relationship is linear. So, your constants m, k and c, these elements of vibratory system are having constant coefficient values k, m and c. As long as they are constants, the governing equation of motion is linear. Okay. So, with that assumption of a linear system, linear vibratory system, so linear vibratory system has a property that if you move this linear vibratory system with an excitation force having a period capital T, the response is expected to be at the same period of oscillation, right. So, when the excitation force f of t has excitation or repetition rate and the frequency omega, then your response x of t will also have the response which is given by omega. Okay. Of course, this will get slightly modified, we will discuss that in detail, and of course, the response will be with some amplitude, we do not know what that amplitude is, but definitely one thing is for sure, that for a linear vibratory system like what we are discussing, if you excite it with the frequency omega, the response will also be with the same frequency, that is omega. Now, So, the assumption here is that we shall since we have decided to stick to complex notation, the assumed solution. Okay. So, we assume the solution the way we have also done it in a free vibration case. Assume the solution of this equation to be given by an unknown amplitude and frequency, of course, for a linear system, the same frequency as the frequency of excitation. So, we assume complex harmonic response capital X e to the power j omega t. Okay. So, that is an assumption. With this assumed response we will continue further. So, we in today's lecture have seen how the response to an arbitrary excitation which is not a sustained kind of an excitation is obtained, and in that context we discussed in detail how the Duhamel's integral or a convolution integral is useful in obtaining the response. The questions based on the topic we discussed are these. So, please try and attempt these questions to recollect all the concepts that we learnt in this lecture. As usual, the answers follow in this slide.